So we have now the next talk that is going to be presented by Professor Vincenzo Giannini from the Technology Innovation Institute, Extraordinary Transparent Compact Metallic Metamaterials. So Vincenzo, the floor is yours.
Thank you, everyone. I'm really happy to be here. And I'm Vincenzo Giannini. I will speak to you about a really specific topic today, something that we recently, let's say, observed and analyzed, that is something that we can call transparent metals and how you can do a transparent metal. Overall, I would say in general, I work in other, let's say, topics more than transparent metals because kind of new. I work in phonopolaritons, topological nanophotonics, quantum plasmonics, several problems connected with condensed matter theory. But in this case, we will focus on something particular, something connected with the metamaterials, if you want, and particularly in how we can make a metal transparent. Okay. Let's see. How born actually this project has a long time. We started a couple of years ago or more, I mean, with a student at Imperial College in a group meeting, and we were just speaking about a movie, so a Star Trek movie, where there is a certain point, one of them say that if you could make transparent aluminum, because they need transparent aluminum, you would become rich beyond any your imagination. Well, we did, but I'm still not so rich. So, well, let's see. Anyway, just in order to introduce the idea is, let's speak first a bit on what is a metal and what is a dielectric in a kind of simple way. So when we speak about metal, we think in an object that has, if you want, a core of ions, positive ions, and electrons that are free to move. Now, if these electrons are free to move, when you apply an electric field, let's say a static electric field, what will happen? This electron will move and will screen the field inside. This means that when you apply an electric field to a metal, what you have zero field inside because it's screened, because the electron can cancel the field inside. What's happening when you have a dielectric? When you have a dielectric, actually, what we have are molecules. So you have a crystalline structure, if you want. You apply an electric field. Each molecule will rotate, will alienate, will polarize. And what the final result is that in one phase, let's say you have a negative charge, and the other phase a positive one. And this means that you will have a kind of capacitor, if you want. This means that inside your material, you will have a net field. So that given by epsilon time the electric field outside. So this is a big difference between a metal and a dielectric, if you want. So a metal screen the field, so the field inside is zero. A dielectric actually has a field inside that's proportional to its dielectric constant. Practically, what does it mean? It means that if you shine light on a metal, what you have is a mirror, because the light cannot penetrate in the metal, so it's reflected. And this is a typical metal. And when you have, let's say, a dielectric, what you see that they are transparent, because light can penetrate, will have a field inside, they can go out, so you are usually transparent. For example, glass is a dielectric. Now, the question that we asked was, is it possible to have a material that has both property? Let's say it can be conductive as metal, but transparent as a dielectric. And well, we start to think, and this was actually a group meeting, and we realized easily that, well, maybe there is a simple idea. I mean, let's imagine the material made in this way, where each component of material is a nanoparticle, a metal nanoparticle, in such a way that this metal nanoparticle is not touching the next one. It can be really close, but it's not touching. What you do in this way is a material that can be metallic. I mean, you can metal as much as you want. For example, imagine that this was cubic, you can have really small gaps. But at the same time, when you apply an electric field, this will polarize, in this case, a single sphere, a simple, let's call meta atom, but you will not have electron going through one sphere to the other one. So the idea is, well, this effectively should be the same than dielectric. will be a metamaterial made with metals, but with dielectric properties. So we start to analyze this. We started to do some calculation. The first calculation that we did, just in order to be sure that was right, we did a 2D simulation. We had to write our code because actually we were interested in very compact metallic structure. So you see here you have 2 nanometer gaps and a particle is 38 nanometer. And these are just cylinder of different metals. And what we did, I will not go into detail, but what we did was to solve the band structure of this object, to go to the low frequency region, and from there extract the effective refractive index. The effective refractive index will be complex, and these are the results for different materials. So when you have aluminum, silver, gold, or titanium. What you can see here is the real part and the imaginary part of the refractive index versus the wavelength. And the wavelength is going from 2 micron to, well, 240 in this case. The interesting thing is this. The effective refractive index of this object is positive. So you have 2.8. That is not what's happening with a metal that usually is below 1. So our first guess was right. With this kind of idea, you can take metals, you can pack and get a dielectric. And what you can see here also is that they have also a really quite small imaginary part. Particularly if you check titanium, this the imaginary part is very small. This means that's transparent because of course you can have a positive dielectric constant, but you also want that the light is going through without too much absorption. And these were surprisingly transparent. The reason you can see can be seen here actually, because after certain wavelength, your metamaterial became, the optical response became flat. For Karman scrolling, this means that the imaginary part has to go to 0. That means that it's transparent. So we're really surprised, and we start to study this topic that almost came out just for as a joke, and we started to analyze this kind of structure. So this is again the 2D, because you have a cylinder, and when you analyze this, obviously you can have the electric field that is impinging here, that is aligned to your cylinder, or can be perpendicular to your cylinder, and the response is completely different. So in one case, when it's perpendicular, you have the idea that I told you of the meta atoms. This gives you a positive refractive index, this is the red line, a really small imaginary part. While if you go on the other side, this became a mirror. So with one polarization, you see a dielectric, and the other polarization, you see a mirror. And this is given, well, you can see it in the epsilon that is negative and very big. So this means that in some way you have a polarizer here. Or if you do a 3D one, so you compact in this way. Let's say this case, I think, was titanium with a gap of 2 nanometer and diameter of 20 nanometer, and you make the same analysis. What you see again is a peak here in the region of more or less around 2 micron, very close to the visible region, and later this gone to 4.9, and this became the effective refractive index for all this wavelength of your metamaterial. In particular, what we realized that you can have very compact metamaterial, and you will get an effective dielectric constant that's even more transparent than materials germanium. That is a very well-known transparent metamaterial. So practically you can build up a new material. In particular, what you also discovered that playing with this gap, if you are able to do it very small, you can get an n, a positive n that's very big. So you can have also 10, 20, that are refractive index that you don't have in nature. So you can build a new material with a really high refractive index that doesn't exist in the world, that doesn't exist in nature. In order to see if, to analyze this kind of structure, we decided that I will show you, just to convince you that what will happen if you take a sphere, let's say, made with a lot of tubes, and what I will show you is a kind of analysis of this object when the light is impinging on top of it, and this is with metallic nanostructure. It is effective medium, just to show you that the idea of the effective medium actually works, and is it transparent, because at least for us was quite surprising. So here what I plotting here is the absorption cross section of this two structure, and you can see that we have exactly the same result. So this is the effective medium, and this is the real material made with a lot of dielectric, if you will, with a lot of metals. You see modes, here, same modes. There is some small difference around 2 micron. Later we'll explain why, but for the rest of the spectra, we have exact, well, just because here is breaking down the effective medium theory, is working very well, the effective medium approach. In particular, what you can notice here are exactly this mode. What are these modes? These modes are what are called, are practically kind of me mode in this kind of structure. So these are whispering granularity mode. And you can look, for example, the field inside, and you see, so this is the, was the mode A. So you can even see the small cylinder inside this structure. That is the same that you get when you do the effective medium. So practically this for mode B, and you can see here mode B. This is the C, that is here, and D, and that's here. So what I'm telling you here is that the idea of the effective medium worked very well, first. Second, that a metallic block of material, compact metallic block, give you a transparent or a dielectric behavior. And this is quite interesting because now you can start to play and now you can start to think what you can do. One of the first things that we tried, just to for fun, was to make a kind of lens. Let's say that you make a lens with this material and you compare with a solid lens made with aluminum. You make a solid aluminum, you take a cylinder in this case, and this is the effective dielectric constant. So here what you see is just diffraction. This lens will not work. Practically you have a mirror here, and this actually can see below here also even some surface plasma, but what you see here is just diffraction. You don't see any focusing effect. While here you see a focus. This is the focus of a lens in the near field. And this is the same with the effective dielectric constant that was in this value in this case. So these two images, they present the same near field. So means that you can avoid this really big simulation and work directly with the effective value when you have it. And at the same time tell you that you can build something as a lens with a metal. And this can be interesting, for example, in the terahertz. The terahertz, you don't have so much good lenses, so you could do a lens that is metallic, that is thin, that we will see later, it can be achromatic, and have a lot of property that can have a big refractive index that usually you will not have and can have in technological application. Another thing is that you could do is what is called a green lens. So an object, so you can change locally the dimension of your particles. And if you do that, and if you do in a particular way, you can get, for example, a refractive index that is as a kind of square behavior. If you do that, it's possible to show that this is a lens that will focus the light in a point for any angle that you, for every direction that you do. This is quite interesting because you could use this for nonlinear effect, for example, because if you think, if you have a look to this point here where you are focusing the field, well, here you have a lot of metallic cylinder or metallic particle, but the gap within them is 2 nanometer, and this, the wavelength here was 2 micron, I think, yeah. So this means that you are shrinking 2 micron in a gap of 2 nanometer. That means that the field there is really, really high. So you could use this, for example, in order to trigger nonlinear effect. That could be quite interesting. And in particular, when we started this, there is something important to say. One of the first metamaterial actually was something called the artificial dielectric. That were something that I discovered later actually was something similar to what we're doing here. So it was in the 40, and they were kind of material that were you use in the macro way. You can use metallic particle, cylinder, whatever, and you have similar effect. In that case, actually, it's not surprising because in the macro wave, if you want, on that region of the frequency, the metal is behaving as a perfect conductor. So you expect that you will not have absorption, and you can expect this kind of phenomena. What was interesting here is that if you take a real metal, so if you work in a region, for example, in infrared, where the skin depth is of the same order of your particle or even bigger. So this is the ratio, if you want, of this is the diameter of one particle over its skin depth. So here is 1, and here is 10 to minus. So here the skin depth is even 10 times bigger than your particle. What you see is that the effective index became transparent. And so practically, this was the news, real metal can do the job. And another curiosity is that even if it's not precise, you can get a really good idea of what will be the effective refractive index just with a Maxwell-Garnett approach, even if curiously should not work in this region, but it's not really working, but the error is small. And this actually we discovered why. We're going in detail why Maxwell-Garnett works, but this tell you that if you can design using the simple formula, you can design your material and make it very easily. Now, something interesting is that if you change your unit cell, so if you change the shape, if you change the period, if you change the kind of lattice that you have, you can tune the property of your material. So very easily you can have the material, let's say, that you want playing with this kind of parameter, and it works very well, almost very well with any metal. With the, you can see this, pay attention that here this is going from 2.7 to 2.8, so looks that is varying, but actually it's quite flat. And the important thing is that this effect is extremely ultra-broadband. That means the only thing that you need is a good metal and a very big wavelength. And in other words, when you are over 2 micron, that is what you see here, you see that the response, the effective epsilon, refractive index is practically flat, and this the imaginary part is 0. So this material, this means that this material works in the same way at 15 micron, 100 micron, 200 micron, whatever you want. So this is like extremely broadband material, and this actually is usually a problem with the metamaterials, because metamaterials not always, but some usually are based on kind of resonator ideas. That resonator idea works, but works in with a particular bandwidth, with a particular region of frequency. Here, what you see that this is completely broadband. As soon you get the enough big lambda, will work well everywhere. And well, I'm mainly a theoretician, but I like to see what we forecast. And speaking with a colleague in Tarragona, actually, he told that he was able to do this kind of material, and he did a film of very small metal nanoparticle. Here you can see a picture, and he measured the transmission. Now, what you see here is the blue line is the germanium transmission compared with the gold transmission. So it's kind of a 640 nanometer thickness, and if you calculate the reflection, transmission should be almost 0 in this case, but that's what you see here, what you saw, that was close to 100%. So in the real world, this object exists, so we can try to play and see what we can do more. And with this, before I hope that it was not too late, I need to thank the people that helped me with this project, that are Ramon Alvarez Puebla and Miguel Correa Duarte in Spain, that they did the fabrication. And at Imperial London, Stefan Meyer, Richard Craster, Sam, and Xiaofei, that were the 2 PhD students that helped me in that moment. And with that, I conclude saying that with the metal, you can do a really extremely transparent material. So you can have a really extremely transparent metal that could be interesting, for example, maybe, I don't know, in solar cell, in touch screen, maybe, on something like that. You can have, the effect is extremely broadband, it's tunable. You can do practically with any metal, any good metal. You can have really strong enhancement of the electromagnetic field. You can have a high refractive index bigger than what you have in nature. That's quite interesting. And well, I also told you that it's not just a theoretical idea, but there are experiments, so this really works. And with this, I would like to thank you for the attention, and please tell me if you have any question.
Thank you very much. Thank you very much, Dr. Giannini. We have a couple of questions here in the chat. Are you able to read it? From Rafael Santiago, it's Dr. Vincenzo. Okay. Thank you for very interesting presentation. What about the medical properties of the invisible metal? Should it be the same or affected by those gaps?
So say again, what should be?
I guess he's asking if the gaps in the metals are going to interact with organic matter in biomedical applications.
Okay, yeah. Good question, Rafael. I just saw your question now. Okay, it depends what you want to do. So if you can have the interaction, and that I think is something quite good. The idea is, this was one of the idea. Well, the idea is that you can focus so much field that, let's say, if you have a material with some resonance, you can strongly interact with it. And I think this could be interesting some with lasing or with, as I told you, nonlinear effect, these kind of things. Or you can have an inert material that is not having any response in that region, and you is doing just the work of let's say, layer that is separating the two metals. So yes, you can have both. If that was the question, you can have interaction or not, depending on the material.
Okay. Next question is asked here by
level cylinder.
Yeah, exactly. You can read.
Yes, on a non-level cylinder produced, and what technology was used? Okay. This, I mean, I'm not an expert on that particular part, but I think was that was self-assembling, and they were able, and what that was the technique. And I used to bond them together. And what they did practically was, they told me that it was pretty simple. The idea was to take this nanoparticle, cover with a very thin layer, I think it was 1 nanometer of dielectric, that I don't remember what was, but was nanometer, and later let self-assemble this particle and make a film. Okay, so that was let's say, in a simple way, what they did. And the gaps were 2 nanometer, if that was the dimension, and the particle 60 nanometer, I think, diameters. It was gold.
Okay, there is another one by Maya Mansouri. Thanks for the presentation. 2 questions.
Yeah, that actually is a good question, right? Yeah. Of course, I think you could have some effect, right? Let's say that I never realized this. You could have this can be a kind of sensor that's changing the refractive index with if the expansion. I need to check how much will expand in volume, but I guess. Well, I'm thinking it careful, maybe will not affect so much. Will affect only if you are able to change the gap within nanoparticles. If there is something that is not, I mean, let's say if you have a spacing, a layer between them that, let's say, is 1 nanometer, 2 nanometer, nanometer, I don't think, and you don't change it, you will not change it. This will not affect the properties. But if you are able to have this material for some reason, I don't see very well how now, and you can switch the gap, yes, that will be affected.
Okay. And there is a 3rd one. Can you?
Oh, there is another one. Thank you for
the last one. There is one at the end. If we care about visible wavelength range, why are we looking at the wavelength in the range of 50 to 150 micrometers?
Because I was not caring about the visible. Actually, the visible is where it works. Worse. This idea, because you have plasma resonance that enhance the absorption. My idea actually here was not really the visible, was I was speaking, for example, for a metal lens in the terahertz, for an infrared. I mean, a lens that this is the reason, and also because I'm looking there because it's there where it's working. So there is the both, but not definitely the visible. Visible is where it works.
Yeah, interesting application I mean, if you manage to do this in optical range, will be really interesting for many applications.
You are completely right.
Yeah,
but also in terahertz on any infrared, there is nothing. So also there is interesting.
Yeah, definitely. Thank you very much. Very interesting talk and very interesting application of this metamaterial.